At first light, the Great Pyramid does not look like a building with rooms inside it. It looks like a mountain that has learned geometry. Its faces rise from the Giza plateau in vast plains of weathered limestone, each side aligned with a precision that still resists casual explanation, and its mass seems almost absolute. The structure does not invite the imagination inward. It overwhelms it from the outside. Yet somewhere inside that immense body of stone, above the known passages and beyond every route a visitor can follow, modern instruments have detected a region where there is less stone than there should be. That simple fact changes the monument. For centuries, the interior of the pyramid has been described through a familiar sequence of spaces: a descending passage, an unfinished chamber cut into the bedrock, an ascending route, the grand gallery, the so-called Queen's Chamber, the King's Chamber, narrow shafts, and a small number of relieving spaces above the granite room. These features form the internal map most people know. They are the parts that explorers entered, measured, drew, photographed, argued over, and sometimes damaged in the long search for answers, but taken together, they occupy only a minute portion of the pyramid's total volume. Almost everything else is masonry. The scale is difficult to hold in the mind. The pyramid was originally about 146 meters high. Its base covered more than 5 hectares. Millions of stone blocks were placed in rising courses, creating a monument whose weight is measured not in thousands, but in millions of tons. A person walking inside it moves through a handful of narrow channels surrounded by stone in every direction, above, below, and to either side lie distances of solid-looking masonry that no human being has directly inspected from within. Even the known chambers feel less like rooms in a conventional building than bubbles preserved inside a geological mass. This is the first source of the mystery. The Great Pyramid appears heavily explored because its passages are famous, but famous is not the same as complete. The accessible route creates an illusion of knowledge. Visitors enter through a cut in the north face, stoop through sloping corridors, climb toward the center, and eventually stand beneath the enormous roof of the Grand Gallery or inside the polished granite walls of the King's Chamber. These spaces feel conclusive because they are dramatic. They have names, dimensions, photographs, and centuries of interpretation, yet they do not provide a full architectural plan. They provide only a thread through the stone. Before we go deeper, take a moment to like the video and subscribe, if this is the kind of history and mystery you enjoy. The pyramid's interior is also deceptive because the spaces we can reach are not distributed evenly. They cluster along a narrow north-south axis. Large regions of the monument have no known passage leading into them at all. The eastern and western portions are almost entirely inaccessible. Much of the upper core remains beyond direct observation. This does not mean that hidden chambers must be waiting there. Ancient builders could fill enormous areas with masonry and rubble without leaving usable rooms. Gaps can also form through construction methods, shifting blocks, irregular joints, or intentional stress-relieving designs. But it does mean that the absence of a doorway is not the same as proof that nothing exists beyond the wall. For a long time, investigators had only a few ways to test what lay inside. They could follow existing passages, they could examine cracks and joints, they could study the pyramid's outer surfaces and compare its internal design with other monuments. In more aggressive periods, they could tunnel, blast, pry, or bore through stone. Some of the routes now used by visitors were created not by the original builders, but by later people forcing their way into the structure. The famous passage associated with the Abbasid Caliph al-Ma'mun is the clearest reminder. It cuts through the masonry with little respect for the original plan, a scar left by a search conducted before conservation became part of archaeology. Modern research faces a different obligation. The pyramid is not an unopened mound on a remote hillside. It is one of the most studied, visited, and protected monuments on Earth. Any attempt to reach an unknown internal space must confront the possibility that the act of investigation could destroy the very evidence being sought. A drill may cross a painted surface. A probe may disturb fragile salt deposits or loosen a joint that has remained stable for thousands of years. A small opening can change airflow and humidity. Even apparently solid stone may contain fractures, mineral decay, or concealed structural stress. The monument does not merely hide information. It also makes the recovery of that information ethically and technically difficult. That is why the idea of an unreachable space carries such power. It is not simply a room with a locked door. No known door has been identified. No corridor has been confirmed leading toward it. No camera has shown its floor, walls, or ceiling. There is no image of dust lying undisturbed across a hidden chamber, no inscription emerging from darkness, no sealed object waiting in the beam of a lamp. What exists is a difference in density detected through the body of the pyramid. Somewhere above the Grand Gallery, particles passing through the stone behaved as though they had crossed a substantial region containing less material than the surrounding masonry. The correct term remains a void. That word is less dramatic than chamber, but more honest. A void can be many things. It might be a single long space. It might be divided into smaller sections that current measurements cannot separate clearly. It might be horizontal, inclined, or formed from several connected volumes. It could have been designed for structural reasons, created during construction, or intended for a function that has no exact parallel elsewhere in the monument. Scholars still debate these possibilities because the evidence remains incomplete. The signal is strong enough to indicate that a large low-density region exists, but not detailed enough to reveal its architecture. This distinction matters because the Great Pyramid has always attracted stories faster than evidence. Empty areas become secret chambers. Unexplained corridors become routes to lost archives. Any unknown volume is quickly assigned a king, a treasure, a body, or a forbidden technology. The monument's reputation almost demands a spectacular answer. Yet the deeper scientific story is more interesting precisely because it resists that temptation. A structure examined for centuries still contains a feature large enough to alter its internal map. And the discovery did not come from breaking through a wall. It came from learning how to observe what stone normally conceals. The Big Void, as the research team cautiously named it, exists at the meeting point of ancient engineering and modern uncertainty. Its presence reminds us that the pyramid is not a transparent object. The masonry hides not only possible spaces, but also the sequence of decisions made by its builders where they changed plans, where they redirected weight, where they left gaps, where they sealed routes, and where they created forms that later generations no longer understood. Every known chamber is part of that vanished logic. Every unknown region raises the possibility that the surviving plan is incomplete. To understand why a large space could remain unreachable for so long, the familiar interior must first be seen without the comfort of familiarity. The passages are not a complete tour through the monument. They are a narrow path through an immense artificial mountain, and each turn reveals how little of that mountain has ever been entered. The route into the Great Pyramid begins with the descent, not an ascent. That detail is easy to overlook because the monument rises so powerfully above the plateau, yet its oldest known internal path leads downward through the north face and into darkness. The original entrance sits high above the present ground level, framed by enormous limestone blocks arranged to redirect weight. From there, a narrow passage slopes through the core masonry and toward the bedrock beneath the pyramid. The angle is steep enough to make movement awkward, and the dimensions force most visitors to bend. The effect is immediate. The pyramid's vast exterior gives way to confinement. Far below the centre of the monument, the descending passage reaches a rough subterranean chamber carved into the natural rock. It is unfinished, irregular, and unlike the carefully shaped rooms higher above, a trench cuts into its floor, and part of the chamber looks abandoned before completion. Whether this was an early burial plan, a symbolic underworld space, or a stage in a changing design remains debated. What survives suggests interruption rather than fulfillment. The room proves that the internal scheme developed in relation to the ground beneath the pyramid, not only within the stone piled above it. Partway down the descending route, another passage breaks upward. This ascending passage was originally blocked by heavy granite plugs, making it inaccessible from the main entrance. Later intruders reached it by cutting around those barriers through softer limestone. Beyond the plugs, the route climbs toward the heart of the pyramid and divides into several connected paths. One continues horizontally toward the chamber long called the Queen's Chamber, while the other opens dramatically into the Grand Gallery. The Queen's Chamber is neither known to have belonged to a queen nor proven to have served as a burial room. Its traditional name comes from later interpretation, not from an inscription. The chamber lies close to the pyramid's central vertical axis and has a pointed, corbelled roof. Its walls are limestone, and a niche in the eastern wall rises in a tall stepped form that has inspired theories ranging from a statue recess to a symbolic feature or concealed route. No single explanation fully accounts for it. The chamber also contains two narrow shafts that begin inside the walls, but originally did not open into the room. When investigated in modern times, they were found to extend upward and then stop at small blocking stones, adding another layer to the pyramid's internal complexity. From near the Queen's Chamber corridor, movement toward the upper rooms returns to the Grand Gallery. Few interior spaces in ancient architecture produce the same sensation. It rises steeply for more than 40 meters, with walls that narrow upward through successive corbelled courses. The floor contains a central channel flanked by raised benches, and rectangular sockets appear at regular intervals along the sides. The gallery is both passage and monumental interior, engineered on a scale far beyond what was necessary for simple movement. Its purpose is still debated. Some interpretations connect it to the handling of granite blocking stones, others to construction logistics, ritual design, or structural planning. What is certain is that it forms the largest known open volume inside the body of the pyramid. At the upper end of the Grand Gallery, the space narrows again. A low passage leads through a small antechamber constructed partly from granite. Slots and grooves suggest a system of barriers or portcullis stones intended to restrict access. Beyond it lies the King's Chamber, the most famous room in the monument and the one most often assumed to have been Khufu's intended burial chamber. Its walls, floor, and ceiling are built from massive blocks of red granite transported from Aswan, hundreds of kilometers to the south. A granite box, usually called a sarcophagus, stands near the western wall. It is too large to have passed through some completed access routes, implying that it was placed before the surrounding construction was finished. The room is austere. There are no surviving painted scenes, carved funerary texts, or treasure. Its emptiness has encouraged endless speculation, but emptiness, after more than 4,000 years is not surprising. Robbery, reuse, and disturbance affected royal monuments throughout Egyptian history. Still, the lack of inscriptions means that even the chamber's exact ritual role must be inferred from architecture, comparison, and context. 2 shafts rise from its northern and southern walls and reach the exterior of the pyramid. They are often called air shafts, though symbolic or ritual functions may also have mattered. Their precise purpose remains uncertain. Directly above the king's chamber is a stack of 5 low spaces, often called relieving chambers. They are difficult to access and were not designed for ordinary movement. 4 have flat granite ceilings, while the uppermost is covered by a pointed arrangement of limestone blocks. Their practical effect is to redirect some of the enormous weight above the chamber, protecting the granite roof below. These spaces preserve quarry marks and crew names painted on blocks, evidence left by the people who built the monument. Their presence is a crucial reminder that not every empty volume inside a pyramid was intended to be entered or seen. Some spaces existed because architecture demanded them. A separate opening known as the well shaft connects areas near the Grand Gallery with the lower descending route. Its irregular course passes through masonry and bedrock, and its function is uncertain. It may have served as an escape route for workers after blocking stones were placed, a construction access path, ventilation, or more than one purpose over time. Like several parts of the pyramid, it does not fit comfortably into a single explanation. When all these spaces are drawn together, they create a complex but surprisingly thin internal network. The known passages form a narrow branching line concentrated near the central axis and northern side. They do not spread through the pyramid like corridors in a palace. There are no known suites of rooms filling the eastern or western mass, no broad stairways connecting multiple levels, and no regular pattern of chambers repeated through the structure. Most of the monument remains inaccessible stone. This map is essential because the Big Void does not appear in isolation. Its detected position places it above the Grand Gallery, in a region long assumed to be solid masonry. It does not coincide with the King's Chamber or the known relieving spaces. It is not the Queen's Chamber, not one of the shafts, and not the corridor behind the north-face chevrons. Its signal belongs to a different portion of the pyramid's internal body. The familiar rooms therefore provide both context and warning. They show that the builders created spaces for burial, movement, blocking, symbolic alignment, construction, and structural protection. They also show how misleading modern names can be. A so-called chamber may not have held a burial. A so-called air shaft may have served ritual purposes. A low cavity may be structurally essential despite never being meant for human entry. As investigators consider the unreachable space above the Grand Gallery, every known feature argues for caution. The pyramid contains rooms, corridors, shafts, gaps, and stress-relieving volumes, but their forms do not automatically reveal their functions. Seen in section, the interior resembles a delicate arrangement of openings suspended inside an overwhelming mass. The accessible route gives a sense of progression, yet it also reveals the limits of physical exploration. Each chamber ends in stone, each shaft narrows beyond reach. Each wall may conceal construction details no eye has seen since the blocks were set in place. The map is real, but it is not necessarily complete. Stone conceals because it does not merely surround the known rooms, it overwhelms them. The passages of the Great Pyramid are narrow exceptions inside an immense load-bearing body, and the farther one moves from those exceptions, the less direct evidence survives. A wall may be 1 block thick or several meters thick. A joint may mark the edge of a chamber, the seam between adjacent stones, a later repair, or nothing more than the irregular fit of masonry, even where an investigator can stand close enough to touch the surface. The visible face reveals almost nothing about what lies behind it. The pyramid's core is not a single homogeneous substance. It is composed of limestone blocks of different sizes, shapes, densities, and conditions, arranged in courses that are regular in some places and less predictable in others. Voids between blocks can be narrow or uneven. Mortar fills some joints. Rubble and packing material may occupy internal gaps. Natural fractures run through certain stones, while others carry weathering or mineral alteration that developed over thousands of years. To a scanning instrument, all these differences matter. A low-density signal might indicate open air, but smaller anomalies can also result from cracked stone, loose fill, poorly bonded joints, or a change in material. The monument hides architecture inside geological noise. This is one reason conventional exploration reaches its limits so quickly. A person can follow a passage, inspect a ceiling, measure an angle, and record the dimensions of a chamber, but once the route terminates, physical observation stops. The wall ahead may conceal a continuation, yet it may also be several meters of solid masonry. Without excavation, there is no simple way to tell. The pyramid was not designed with maintenance corridors, inspection hatches, or construction drawings preserved for later readers. Its internal organization was created for ancient purposes, then sealed inside a structure whose own weight became part of the barrier. The scale of that barrier is easy to underestimate. In an ordinary building, a hidden room might lie behind a wall a few tens of centimeters thick. Inside the Great Pyramid, an unknown space may be separated from an accessible chamber by many meters of limestone. Between the grand gallery and the exterior surfaces lies a vast triangular mass of stone. Between the gallery roof and the upper courses above it, the masonry is not arranged as a thin shell but as part of the monument's structural body. Reaching a suspected void could require crossing multiple blocks, whose orientation, condition, and relationship to surrounding loads are not fully known. The Grand Gallery makes this problem especially difficult. Its corbelled walls rise inward course by course, narrowing the space toward the roof. This design transfers forces away from the open passage below, but the exact arrangement of masonry beyond the visible faces cannot be traced by sight. The gallery may be surrounded by carefully arranged blocks, irregular packing, or additional structural features. A cavity above it could relate to the way weight was redirected. It could also belong to a construction system no longer visible from the finished interior. Scholars still debate how much of the pyramid's hidden architecture reflects permanent design, and how much preserves temporary stages in the building process. Temporary space is itself a useful possibility. Large monuments are rarely assembled as though every block moves directly from quarry to final position without intermediate systems. Builders need access routes, working surfaces, lifting zones, storage points, and places where materials can be maneuvered. Some of these spaces are removed or filled when construction ends. Others may remain trapped within the final structure because sealing them is unnecessary, difficult, or structurally undesirable. An inaccessible cavity could therefore be the fossilized trace of construction rather than a chamber created for ritual or burial. Yet the opposite possibility cannot be dismissed. The known interior demonstrates that the builders deliberately created spaces with highly specific forms. The grand gallery, the granite chambers, the narrow shafts, and the relieving spaces above the king's chamber are not accidental gaps. Their dimensions and positions reflect planning. If the big void has a coherent shape, consistent orientation, or architectural relationship to the gallery below, it may belong to the same deliberate system. The difficulty is that the present evidence does not reveal enough detail to distinguish a carefully built corridor from a chain of connected cavities. Blocked routes make the problem more complicated. The ascending passage was concealed behind granite plugs. The original entrance was hidden beneath casing stones and masonry. Shafts in the Queen's chamber began behind intact wall surfaces. The monument therefore contains confirmed examples of features that were intentionally inaccessible or invisible from the finished rooms. This does not prove that every anomaly is connected to a sealed passage, but it shows that absence of visible access cannot be treated as decisive evidence against one. Over time, structural movement adds another layer of uncertainty. The pyramid has survived earthquakes, temperature changes, stone loss, quarrying of its casing, and repeated human intrusion. Blocks have shifted slightly, cracks have opened, repairs have altered some surfaces. A space that was once connected to a narrow route might now be cut off, while a joint that appears ancient may have widened long after construction. Studies of the monument's dynamic behavior show that chambers and relieving spaces influence how forces move through the structure. This means any hidden volume must be considered not only as archaeology, but also as part of a living mechanical system that continued to respond to stress. Even the term solid stone can mislead. The pyramid is solid in the everyday sense that it is overwhelmingly masonry, but it is not a seamless, artificial mountain. It is an assembly of individual blocks. At its scale, the spaces between those blocks form a hidden landscape of seams, fractures, pockets, and changes in density. Most are too small to matter architecturally. Some may be large enough to affect measurements. A very large and persistent anomaly, confirmed from different positions, stands apart from this background, but understanding its boundaries still requires separating open volume from the complex texture of the surrounding core. This is why destructive investigation is so tempting and so dangerous. A borehole could provide a direct answer at one point, yet the chosen path might miss the space, enter it through an unstable surface, or damage a feature that cannot be replaced. Drilling also creates only a narrow line of information. It can show what lies along the bore, not necessarily the full geometry of the void. Before any such intervention, researchers need confidence about location, distance, orientation, and structural risk. The stone demands that certainty while withholding the evidence needed to obtain it. The pyramid therefore preserves its unknown spaces through a combination of mass, complexity, and conservation. It is difficult to see through, difficult to enter, and too important to treat carelessly. Every method must negotiate between curiosity and restraint. The inaccessible regions remain hidden, not because modern investigators lack imagination, but because the monument turns even a simple question into a problem of physics, engineering, archaeology, and ethics. For most of history, the stone won. Explorers could enter only where an opening already existed or where they were willing to force one. The possibility of observing deep internal space without cutting through the monument required a different kind of vision, one based not on light passing through a doorway, but on signals capable of crossing stone itself. The search for hidden space inside the Great Pyramid changes completely when destruction is removed from the list of acceptable tools. Once investigators can no longer cut freely through masonry, pry apart joints, or tunnel toward every suspected anomaly. the problem becomes one of indirect vision. The monument must be questioned without being opened. Its answers arrive not as a doorway, but as heat patterns, reflected waves, electrical contrasts, changes in vibration, and particles passing through stone. No single method can reveal everything. Each responds to a different physical property, and each has limits shaped by distance, material, access, and the complex construction of the pyramid itself, used carelessly. A scan can produce an ambiguous patch that invites more interpretation than the evidence supports. Used together, however, several independent methods can turn uncertainty into a progressively sharper map. Infrared thermography is among the most visually immediate. Stone warms and cools in response to sunlight and changes in air temperature. A solid wall should generally follow one pattern, while a cavity, a hidden opening, a different type of block, or a poorly bonded zone may alter the way heat moves through the surface. By recording temperatures across the pyramid's exterior or interior walls at carefully chosen times, researchers can look for areas that warm or cool differently from their surroundings. The attraction is obvious. Nothing needs to touch the stone. Cameras can observe broad surfaces quickly, and unusual thermal behavior may point toward features worth investigating with other instruments. Yet thermal anomalies do not identify their own causes. A temperature difference may result from an airspace, but it may also reflect surface weathering, changing sunlight, wind exposure, moisture, cracks, repairs, or differences in stone composition. Thermography can reveal that something behaves unusually, not necessarily what that something is. Ground-penetrating radar approaches the monument differently. A radar unit sends electromagnetic pulses into material and records the echoes produced when those signals encounter changes in electrical properties. In favorable conditions, the reflections can reveal interfaces, voids, fractures, and boundaries between different materials. Radar is widely useful in archaeology because it can create subsurface profiles without excavation. But limestone masonry is not a simple medium. Irregular blocks, mortar joints, rough internal surfaces, and changing moisture levels can scatter the signal and make interpretation difficult. Its effective range is also limited. Radar works best when the suspected feature is relatively close to an accessible surface. This made it especially useful in investigations of the North Face corridor, where the unknown space lay behind the chevron blocks near the pyramid's outer face. There, researchers could scan from a practical distance and compare radar results with other techniques. The Big Void is a different challenge. It lies deeper within the monument, above the Grand Gallery, beyond a thickness and complexity of masonry that make conventional radar far less decisive. Ultrasonic testing uses mechanical waves rather than electromagnetic ones. A transducer sends high-frequency sound into stone, and the returning signals reveal changes within the material. Reflections can mark the back surface of a block, a fracture, a joint, or a transition into a cavity. In the King's Chamber, modern phased-array shear-wave equipment has been used to examine accessible granite blocks and detect reflective surfaces several meters behind the visible walls. By changing the angle and timing of multiple ultrasonic elements, researchers can build a more systematic image of features that cannot be seen directly. This kind of work demonstrates how much information can be recovered from apparently solid walls without drilling. It can help determine block thickness, locate joints, and identify internal anomalies. But sound waves also weaken and scatter as they cross multiple boundaries. Granite, limestone, mortar, air, and fractured stone transmit vibration differently. A clean signal from within one block may become far harder to interpret after crossing several courses of irregular masonry. Ultrasound can look deeply into selected surfaces, but it is not a simple camera capable of photographing the entire pyramid from one room. Electrical resistivity tomography adds another contrast. Electrodes introduce a controlled electrical current and measure how strongly the material resists its passage. Dense stone, moist zones, fractures, fill material, and open air can produce different resistivity patterns. By combining many measurements from different positions, researchers can calculate a model of what may lie beneath or behind a surface. This technique was later applied directly to the north face corridor. It helped distinguish an air-filled region behind the chevron area and contributed to a clearer model of the hidden structure. Its value lay not merely in producing another image, but in testing whether a feature detected by one method appeared through a completely different physical principle. When radar, ultrasound, electrical resistivity, and muon measurements all point toward the same location, the chance of a single instrumental illusion becomes much smaller. Image fusion is the step that brings such methods together. Instead of treating every scan as a separate picture, researchers align the datasets within a common three-dimensional model. A radar reflection can be compared with an ultrasonic boundary. A resistivity anomaly can be checked against a muon signal. Areas where several techniques agree become stronger candidates for real architectural features, while contradictions reveal where interpretation remains uncertain. The North Face corridor provides the clearest example of this gradual process. Muon detectors first indicated an unknown low-density region behind the northern chevrons. Radar and ultrasonic measurements refined its position. Numerical modeling and a later electrical resistivity work helped clarify its dimensions and identify a safe target for further investigation. Only after years of independent confirmation was a very small opening approved. An endoscopic camera then entered and showed an actual corridor. That sequence is important because the camera image did not make the earlier scans unnecessary. The scans made the camera possible. Without them, drilling would have been guesswork. Researchers needed to know where the space began, how far it lay behind the surface, and where a tiny opening could be made with the lowest likely risk. The final visual confirmation was the last step in a chain of non-destructive measurements, not the first. The Big Void has not reached that stage. It remains too deep and too incompletely mapped for a comparable intervention. Its broad position is known, and its minimum extent is supported by muon measurements, but its exact boundaries remain uncertain. No combined radar, ultrasound, and electrical model has yet defined a camera entry point comparable to the one used for the northern corridor. The evidence does not show whether there is a nearby wall thin enough to cross, whether the space has a safe surface for entry, or whether any access attempt would intersect a critical structural zone. Conservation research makes caution even more necessary. The visible stone surfaces inside the pyramid are not inert. Salt crystallization, humidity changes, mineral decay, old fractures, and subtle material differences all affect their condition. A hole only a few centimeters wide may sound negligible beside a monument of millions of blocks, but the scale of the pyramid does not make every intervention harmless. A small bore can cross an ancient joint, expose a sealed environment, or alter airflow in ways that are difficult to reverse. Non-destructive investigation is therefore not merely a technological preference. It is a philosophy of evidence. Researchers try to extract the maximum amount of information while changing the monument as little as possible. The result is slower than tunneling and less satisfying than opening a door, but it protects possibilities that future methods may examine more clearly. Among all these techniques, one has the unusual ability to look through far greater thicknesses of stone. It does not depend on sending a signal into the pyramid. The signal is already falling continuously from the sky, produced high in Earth's atmosphere and passing through the monument whether anyone measures it or not. By counting those particles and watching where too many survive, scientists gained the first clear evidence that the region above the Grand Gallery was not as solid as the old maps had assumed. Every second, invisible particles descend through the atmosphere and pass through the world around us. Most leave no trace that human senses can detect. They cross roofs, hillsides, walls, and sometimes many meters of rock before losing enough energy to stop. Among them are muons, short-lived particles created when cosmic rays from deep space strike atoms high above Earth. They arrive continuously from the sky, moving at nearly the speed of light, and their ability to penetrate dense material makes them useful for a task that would otherwise seem impossible: looking through a stone monument without opening it. A muon is similar to an electron in some respects, but far heavier. That greater mass allows it to travel through matter more effectively. Some muons are absorbed quickly, while higher energy particles can cross hundreds of meters of rock. The amount that survives depends on how much material lies along the path. A thick, dense region blocks more muons. A thinner or lower density region allows more of them to pass. By placing detectors beneath or beside a structure and measuring the directions from which muons arrive, researchers can compare the observed particle count with the count expected from a completely solid model. The principle resembles medical imaging only in a broad sense. An X-ray machine sends radiation through the body from a controlled source, while mammography relies on particles that nature already provides. There is no artificial beam fired into the pyramid. The sky is the source, and the monument itself becomes the object filtering that particle rain. Detectors record where the muons came from and how many crossed a particular line through the stone. If more particles arrive from one direction than the model predicts, the most likely explanation is that they encountered less material along that route. This sounds straightforward, but the practical work is slow. Muons are abundant on a global scale, yet only a limited number pass through any small detector at useful angles. A detector must remain in position for weeks or months to collect enough events for a statistically meaningful image. The thicker the stone, the fewer particles survive. The deeper the suspected space lies inside the pyramid, the more carefully the data must be gathered and compared. Researchers are not watching a picture appear instantly on a screen. They're accumulating individual particle tracks and building a probability map from them. The detector must also know direction. Simply counting all muons would reveal little. What matters is identifying the path each particle followed through the monument. Different technologies accomplish this in different ways. Nuclear emulsion films record microscopic trails produced by charged particles passing through specially prepared layers. Scintillator detectors create flashes of light when a muon crosses them, allowing electronic systems to reconstruct its trajectory. Gas detectors register electrical signals as particles ionize the gas inside carefully arranged chambers. Each system has its own advantages, sources of error, and methods of analysis. Using several technologies is essential because the Great Pyramid is not a controlled laboratory object. Its external shape is known with great precision, but its internal density varies. Limestone blocks, mortar, granite structures, existing chambers, passages, and irregular joints all influence particle transmission. Researchers must create a model of the monument that includes every known open space. They then calculate how many muons should arrive at the detector from each direction if the rest of the pyramid is filled with expected masonry. Known chambers provide a useful test. If the system is working correctly, the detector should recognize the Grand Gallery, the Queen's Chamber, or other open regions already mapped. These spaces create excess muon counts because particles pass through air rather than solid stone for part of their journey. When the known architecture appears in the reconstructed data at the correct location, confidence in the method increases. An additional excess where no space appears on the conventional plan becomes much harder to dismiss. The resulting image is not a photograph. It does not show stone surfaces, inscriptions, objects, dust, or doorways. It is closer to a shadow map built from density differences. Bright or emphasized regions represent directions where more muons arrive than expected. From the detector's viewpoint, a long corridor and a compact chamber could sometimes produce similar signals if their total low-density volume along the line of sight is comparable. Two separate cavities aligned in the same direction might appear as one. This is why measurements from multiple positions are necessary. Triangulation narrows the possibilities. When detectors observe the same anomaly from different locations, researchers can compare the crossing lines and estimate where the low-density region lies in three-dimensional space. The more viewing angles available, the more accurately its position and dimensions can be constrained. Even then, resolution remains limited by particle numbers, detector size, distance, and the thickness of surrounding stone. Mography can establish that a substantial void exists without revealing whether its ceiling is flat, corbelled, pointed, or irregular. This distinction lies at the heart of the Big Void. The muon data indicate a large region above the Grand Gallery where the average density is significantly lower than expected. The excess is not a tiny fluctuation caused by an ordinary joint between blocks. It extends over a substantial length and appears in independent measurements. Yet the scans do not show a recognizable room in the way an architectural drawing would. They cannot identify a doorway, because a doorway is a shape defined by surfaces, and the present data do not resolve those surfaces clearly enough. Nor can the particles reveal what, if anything, occupies the space. A room containing wooden objects, broken stone, or scattered material might still appear mostly empty compared with solid masonry. Mography is excellent at distinguishing large differences in density, but poor at identifying small objects within a large cavity. It cannot detect paint on a wall or read a carved name. It cannot tell whether the space was ever entered by ancient workers. It measures transmission, not history. The method also depends on assumptions. Researchers must estimate the density of the surrounding stone and model the monument's geometry accurately. If the core contains unexpected variations in packing or block arrangement, those variations may affect the calculated background. This is why the Big Void was not accepted because of one unusual patch in one dataset. The finding became persuasive because separate teams, using different detector technologies and different observation positions, recorded a comparable excess in the same general region. Muon imaging had already proved its value elsewhere before it entered the Great Pyramid. Similar techniques have been used to examine volcanoes, search for hidden cavities, inspect industrial structures, and study large archaeological monuments. A famous early experiment in the Pyramid of Khafra during the late 1960s used cosmic ray particles to look for unknown chambers. That survey did not reveal a major hidden space, but it demonstrated that particle physics could be applied to ancient masonry. Decades later, more sensitive detectors and improved computing made far more detailed investigations possible. there is something quietly appropriate about the technique. The pyramid was built to dominate the visible landscape, yet one of its deepest secrets was detected through particles born far above it. The builders could seal passages, conceal entrances, and bury internal decisions beneath millions of tons of stone. But they could not prevent cosmic radiation from passing through the monument. The same mass that makes ordinary exploration so difficult creates the contrast that mography can measure. Still, the method's power must not be confused with completeness. It can reveal absence inside mass, but it cannot explain why that absence exists. It tells investigators where the old plan is incomplete, then leaves archaeology and engineering to confront the harder question. When the first detectors were installed inside the pyramid, researchers were not expecting a cinematic image of a secret room. They were testing whether the particle rain would match the structure they thought they already understood. Above the Grand Gallery, it did not. The investigation that would eventually reveal the Big Void began not with a claim of hidden treasure, but with a practical question: could several non-destructive techniques be used together to examine the Great Pyramid more deeply than conventional archaeology allowed? The ScanPyramids mission was established under the authority of Egypt's Ministry of Antiquities and brought together Egyptian institutions with teams from France, Japan, and other countries. Its strength did not lie in a single instrument. It lay in the decision to make different forms of evidence answer to one another. The pyramid was an ideal target and a difficult one. Its outer geometry was known. Its principal passages and chambers had been measured repeatedly. Its enormous mass provided the density contrast needed for mography. At the same time, the monument's irregular core, restricted interior, heat, dust, narrow access routes, and conservation requirements turned every installation into a logistical exercise. Equipment had to be carried through passages that forced researchers to crouch, positioned without obstructing visitors or damaging surfaces, and left stable for long periods while thousands upon thousands of particle tracks accumulated. The mission began by combining thermal imaging with muon detection and other non-invasive methods. Infrared surveys examined unusual temperature patterns on the pyramid's surfaces, while particle detectors were placed in carefully selected positions inside and outside the monument. The first task was not to announce a discovery. It was to prove that the instruments could recover architecture already known to exist. Inside the Queen's Chamber, nuclear emulsion plates developed by Nagoya University offered one of the most delicate forms of detection. These passive films required no power during exposure. Muons crossing the layered material left microscopic tracks that could later be developed and analyzed. The chamber's position near the pyramid's central axis made it especially valuable. From there, the detectors could look upward through a large portion of the masonry and toward the region containing the Grand Gallery. The plates had to remain in place while cosmic particles passed through both the pyramid and the detector. After exposure, they were removed and processed with automated microscopes capable of reading immense numbers of tiny tracks. Each track carried directional information. Taken alone, it meant almost nothing. Combined with millions of others, it formed a map of how much material lay along different lines through the monument. Electronic detectors provided a second approach. A scintillator hodoscope developed by the High Energy Accelerator Research Organization in Japan, known as KEK, was also installed inside the pyramid. Layers of scintillating material produced small flashes when muons passed through them. By recording which elements were struck and in what sequence, the system reconstructed the direction of each particle in real time. Unlike passive emulsion plates, electronic detectors could be monitored during operation, allowing the team to check stability and data quality as the exposure continued. A third detector system came from the French Alternative Energies and Atomic Energy Commission through its Institute of Research into the Fundamental Laws of the Universe. These gas-based instruments were designed to operate from positions outside the pyramid. When muons crossed the detector chambers, they ionized gas and produced measurable electrical signals. Observing from beyond the monument's walls created different lines of sight from those available inside the Queen's chamber. That difference would later become crucial. Before any unknown feature could be trusted, each detector had to reproduce the known one. The Grand Gallery served as a calibration target. Its great open volume should allow more muons to reach the detectors from its direction than would pass through an equivalent thickness of solid limestone. If the reconstructed data failed to show the gallery, the model, placement, exposure, or analysis would need to be questioned. The known void appeared. From the Queen's chamber, the particle maps revealed the expected excess associated with the Grand Gallery. The instruments were not simply detecting random variations. They were responding to a real architectural space at the correct position. This gave researchers a reference for judging any additional excess nearby. The pyramid itself had become the calibration object. Such validation mattered because muon imaging depends on careful comparison. The expected particle flux changes with angle, because muons arriving from near the horizon have crossed more atmosphere than those descending more steeply. Detector efficiency can vary. Temperature and operating conditions may affect electronic systems. The monument's stone density is not perfectly uniform. Analysts must account for these factors before interpreting a bright region as open space. A result that looks impressive in a raw image may weaken when systematic uncertainties are included. The teams therefore worked independently as well as collaboratively. Different detector technologies produced their own datasets. Separate analysts reconstructed particle directions and compared them with geometric models of the pyramid. The point was not to force several instruments into agreement. It was to see whether agreement emerged despite their different materials, electronics, positions, and sources of error. That process protected the investigation from one of archaeology's oldest dangers, discovering what one hopes to find. The Great Pyramid has inspired expectations for so long that almost any anomaly can become the foundation of a dramatic story. ScanPyramids approach the structure through measurement first. The labels applied to unexpected regions were deliberately neutral. A signal was not yet a room. A low-density area was not yet a chamber. A possible feature had to survive repeated observation before it could enter the architectural discussion. Working conditions inside the monument reinforced that patience. The Queen's chamber is enclosed, humid compared with the plateau outside, and reach through narrow passages. Instruments could not simply be moved at will without affecting orientation and calibration. Their positions had to be surveyed precisely because a small error in angle could shift the apparent location of a distant anomaly. Outside, detectors had to contend with environmental changes and the challenge of observing through even greater thicknesses of masonry. The mission also operated within a framework of Egyptian oversight. ScanPyramids was not an independent hunt conducted secretly around the monument. Permissions, placement, access, and later proposals for closer investigation required coordination with the authorities responsible for the site. This mattered scientifically as well as politically. Any claim about the interior of the Great Pyramid would attract global attention, and the evidence had to be strong enough to withstand scrutiny from physicists, engineers, Egyptologists, conservation specialists, and a public accustomed to sensational announcements. As the months of exposure accumulated, one feature began to resist ordinary explanation. The detectors saw the Grand Gallery where it should be, but they also registered another excess above it. At first, that excess was only a statistical shape in a field of particle tracks. It had no walls, no floor, and no name. The researchers tested whether it could be caused by known passages, the gallery itself, variations in the core, or imperfections in the reconstruction. It remained. The signal appeared at a height and position, not represented on the accepted internal plan. It extended too far to resemble an ordinary joint between blocks. Its scale suggested something substantial, but the first viewpoint could not reveal its exact geometry. A single detector might still mislead. An unknown bias might mimic open volume. The next step was therefore not to declare a chamber, but to ask whether another technology, observing from another place, would see the same absence inside the stone. One by one, the independent systems turned toward that question. The investigation had reached the point where a calibration exercise was becoming a discovery, though the object being discovered still existed only as an excess of particles arriving from darkness above the Grand Gallery. By the time the independent detector systems were compared, the anomaly above the Grand Gallery had become difficult to explain away. The nuclear emulsion films in the Queen's chamber had recorded an excess of muons from a region not represented on the known plan. The electronic scintillator detectors had seen a comparable signal. The gas detectors positioned outside the pyramid, observing through different paths and using different hardware, also found evidence of a large low-density zone in the same general area. 3 technologies, 3 analyses, and multiple viewpoints were converging on one conclusion somewhere above the Grand Gallery. The pyramid contained substantially less material than expected. The result was announced in 2017 under a deliberately restrained name, the ScanPyramids Big Void. The caution in that name was not accidental. The data did not reveal a furnished chamber, a doorway, a roof shape, or a human purpose. They revealed a volume large enough to stand apart from the ordinary irregularities of masonry. Its minimum length was estimated at roughly 30 meters, placing it in the same broad scale as the Grand Gallery itself. That comparison immediately drew attention, because the Grand Gallery is not a minor crack or construction seam. It is one of the largest and most carefully engineered known spaces inside the pyramid. Yet similar scale did not mean identical form. The Big Void might possess a cross-section comparable to the gallery, but the measurements could not determine whether it was one continuous open space, a sequence of adjacent cavities, or several volumes aligned in a way that produced a combined signal. Its orientation was also uncertain. It could run horizontally, follow an incline, or occupy a more complex arrangement above the gallery. Even its full length remained unknown. The scans established a minimum extent, not a complete boundary. This was the strange balance at the heart of the discovery. The evidence was strong enough to change the internal map of the Great Pyramid, but too limited to draw the new feature clearly. In conventional archaeology, a discovery usually arrives through contact. A wall emerges from soil, a doorway appears beneath debris, a chamber is entered, photographed, and measured. Here, the sequence was reversed. Scientists knew that a large, low-density region existed before they knew what any of its surfaces looked like. The Big Void entered history as data before it entered vision. From the Queen's chamber, the excess appeared above the known line of the Grand Gallery. Researchers compared the signal with simulations based on the pyramid's established geometry. The gallery itself produced the expected muon surplus, confirming that the method could recover a large known space. The additional excess remained separate enough to indicate another volume beyond it. When outside detectors observed the region from different angles, their lines of sight intersected in a position consistent with the internal measurements. The significance lay not only in the size of the anomaly, but in its persistence across systems that failed in different ways. Nuclear emulsion films could suffer from processing or track reconstruction errors. Scintillator hodoscopes had electronic efficiencies and alignment uncertainties. Gas detectors faced their own calibration challenges. A single flawed method might produce a false feature. Several independent technologies producing a compatible result made coincidence increasingly unlikely. The researchers reported the detection with high statistical confidence. In the language of particle physics, the signal was not treated as a casual irregularity. It exceeded the level normally associated with random fluctuation. Still, statistical confidence answered only one question: was there a real difference in density? It did not answer the architectural questions that immediately followed. The public response moved faster than the evidence. Headlines transformed the void into a secret chamber almost at once. Some reports suggested a lost burial room, an undiscovered passage, or a concealed space connected with Khufu's funerary equipment. More speculative interpretations imagined treasure, sacred archives, or evidence of an unknown construction technology. The absence of direct images allowed every expectation to occupy the darkness. The scientific paper itself was far more careful. It did not identify the Big Void as a burial chamber. It did not claim that the space contained objects. It did not describe a sealed door or a hidden entrance. It did not establish whether ancient workers could ever enter it after construction. The study demonstrated the existence of a large, previously unknown low-density region. Beyond that, the evidence remained incomplete. Even the word empty requires care. Mography measures average density along particle paths. A space containing a small quantity of debris, timber, tools, or loose material could still appear dramatically less dense than solid limestone. Conversely, a partially filled construction cavity might produce a weaker version of the same type of signal. The method cannot determine whether the volume is perfectly clear, partly obstructed, or divided by thin stone walls that fall below the current resolution. Its location above the Grand Gallery immediately suggested a structural relationship, but this too remained an inference. The gallery already uses corbelled masonry to move weight away from its open interior. A large cavity above it might form part of a broader load management system. It could reduce mass over the gallery, redirect pressure, or preserve a construction arrangement that helped builders complete the upper courses. The relieving spaces above the king's chamber show that Egyptian architects deliberately created hidden volumes to protect important rooms. But the Big Void is positioned differently and appears much larger, so the analogy cannot settle the question. Another possibility was that the void represented a second gallery-like passage used during construction. Some engineering models of pyramid building require internal routes, ramps, counterweight spaces, or temporary corridors. A long inclined cavity might fit such ideas. Yet no confirmed route links the Big Void to the exterior, the Grand Gallery, or another known chamber. A hypothetical construction passage is only useful if its position and geometry correspond to a workable building sequence, and the available scans are still too coarse to demonstrate that. A more conservative explanation proposes that the signal may arise from several smaller spaces associated with the arrangement of blocks over the gallery. Large masonry structures often contain discontinuities that are not rooms in the human sense. Builders may have left gaps between structural elements, used irregular packing, or created separated relieving zones. If several such cavities align along the detector's line of sight, they can resemble one larger volume. No single explanation fully accounts for the evidence, because the data show extent more clearly than shape. The discovery therefore produced an unusual scientific situation. The existence of a substantial void was more secure than any interpretation of it. Researchers could say with confidence that the traditional internal plan was incomplete, but they could not yet replace it with the detailed new plan. The Big Void had position without architecture, scale without surface, and presence without identity. That uncertainty does not weaken the discovery. It defines it. The Great Pyramid had been surveyed, entered, photographed, and argued over for centuries, yet a space at least 30 meters long had remained undetected because no known route led toward it. Its discovery showed that the monument's apparent familiarity was misleading. The passages visible to human explorers were only part of the design, and modern physics had found a feature too deeply buried for ordinary inspection. What the scans revealed was not a chamber waiting conveniently behind a thin wall. They revealed a harder mystery, a large internal volume suspended above the Grand Gallery, separated from every known route and visible only through the behavior of particles crossing stone. Before anyone could ask what it was for, researchers first had to prove that the signal truly belonged to one coherent space. A signal becomes persuasive not merely when it is strong, but when it survives the loss of every convenient explanation. The Big Void did not earn scientific attention because one detector produced an unusual image. It earned attention because separate instruments, placed in different locations and analyzed through different systems, repeatedly pointed toward the same region above the Grand Gallery. This matters because every method carries its own weaknesses. Nuclear emulsion films are passive and highly sensitive, but their tracks must be developed and interpreted after exposure. Electronic scintillator detectors provide real-time data, but depend on stable electronics, careful alignment, and accurate reconstruction of each particle's path. Gas detectors positioned outside the pyramid observe through longer distances of stone and introduce another set of operating conditions. If all three systems had shared the same design, software, placement, or source of error, agreement would have been less impressive. Instead, they reached a compatible conclusion through technologies that measured muons in fundamentally different ways. The first question was whether the excess could be an artifact of geometry. The Great Pyramid is not a simple solid cone. Its faces slope inward, its core density varies, and known passages interrupt the masonry. A small mistake in the model could shift the predicted muon count. If the thickness of stone along a given line were underestimated, more particles might seem to arrive than expected. Researchers therefore compared the data against detailed models that included the pyramid's external form and established internal spaces. The Grand Gallery offered the most important internal reference. Because its position and approximate volume are known, it should appear in the muon data as a clear excess. It did. This gave the teams a built-in test of scale and direction. The detectors were able to recover a real architectural feature through the same mass of masonry that concealed the unknown one. The additional signal appeared beyond the gallery's expected outline rather than simply enlarging it in a random direction. Another possibility was detector misalignment. A small angular error can become a large positional error when projected through tens of meters of stone. Each system therefore required precise surveying. Its location inside or outside the monument had to be known, along with its orientation relative to the pyramid's geometry. Independent measurements from separate positions helped expose such errors. A misplaced or tilted detector might produce an anomaly from one viewpoint, but it would be unlikely to make different lines of sight converge consistently on the same hidden region. Particle statistics posed a different challenge. Muons arrive naturally and irregularly. Over a short exposure, random variation can create apparent clusters. The cure is patience. Detectors remain in place long enough to gather large datasets, and analysts compare the observed counts with the range expected from chance. The Big Void signal persisted as exposure increased. Rather than fading into statistical noise, it became more clearly defined. Systematic uncertainty is harder to eliminate than random noise. Changes in detector efficiency, temperature, data filtering, or reconstruction algorithms can bias an image. This is another reason the use of multiple technologies was so important. A temperature-related electronic effect in one instrument would not reproduce itself in passive emulsion films. A processing issue in the film analysis would not automatically appear in a gas detector outside the pyramid. Agreement across systems narrowed the space available for a common mistake. The outside measurements were particularly valuable because they viewed the suspected region through a different geometry. Detectors inside the Queen's chamber looked upward from beneath the anomaly. External systems observed it along longer and more oblique paths. If the internal excess had resulted from an incorrectly modelled nearby feature, the outside view might not have confirmed it. Instead, the independently reconstructed lines pointed back toward a compatible volume. This did not produce a perfect three-dimensional image. The viewing angles were still limited, and the thickness of the pyramid reduced resolution. Yet the overlap was sufficient to establish that the anomaly belonged to the monument rather than to one instrument. In effect, each detector saw a different shadow cast by the same missing mass. The distinction between detection and interpretation remained essential. Several instruments could confirm that a low-density region existed without agreeing on its exact boundaries. A long-inclined void, a horizontal cavity, or several connected spaces might all produce partially similar projections. The available measurements constrained the location and minimum size more effectively than the detailed shape. What survived in the record of particles suggested substantial open volume, but not a complete architectural drawing. This is where popular expectations often collide with scientific method. A person shown a bright region in a scan may naturally imagine a chamber with 4 walls and a flat floor. The data do not justify that image. Muon detectors measure how much material lies along a path. They do not directly identify surfaces. The resulting reconstruction is shaped by mathematics, detector resolution, and the number of available angles. A sharp doorway in reality may appear blurred. 2 nearby cavities may merge. A narrow stone partition may disappear within the uncertainty. Even the estimate of roughly 30 meters describes a minimum length, not a final measurement of the void from end to end. The signal extends over at least that distance, but parts of the space may continue beyond the best resolved region. Its cross-section was compared with that of the Grand Gallery because the particle excess suggested a similar order of magnitude, not because the scans revealed an identical corbelled corridor. The strongest conclusion was therefore also the narrowest. A large, previously unknown low-density region exists above the Grand Gallery. Its presence is supported by independent detector technologies and analyses. Its purpose, precise form, access route, and contents remain unknown. That phrasing may sound restrained beside the monument itself, but restraint is what makes the finding durable. The history of pyramid research contains many claims built on incomplete observation. Passages have been assigned symbolic meanings without clear evidence. Cracks have been interpreted as sealed entrances. Irregularities have become proof of chambers that never appeared. The Big Void differs because its existence does not depend on one suggestive mark or one favoured theory. It emerges from repeated measurements. The process also shows why modern archaeology increasingly values convergence. One technique can identify a possibility, a second can challenge it, a third can show whether the first two were detecting the same physical feature. The north face corridor would later demonstrate this sequence more completely, as seismography, radar, ultrasound, electrical measurements, and finally a camera built a chain from anomaly to visible architecture. The Big Void has completed only the earlier stages of that chain. For now, its evidence remains strong but indirect. No photograph has replaced the particle maps. No probe has settled the geometry. The void is known through agreement between instruments that never touched it and never illuminated it. That agreement gives confidence that the space is real, while the lack of direct access preserves almost every question about what kind of space it is. The mystery no longer lies in whether something interrupts the masonry above the Grand Gallery. It lies in the fact that a structure of such scale can be detected from several directions and still remain completely unseen. A visible room can be studied through its entrance, its walls can be measured, its floor examined, and its relationship to neighbouring passages traced directly. The Big Void offers none of these ordinary advantages. It occupies a known region of the pyramid without presenting a known way into it. No doorway opens from the Grand Gallery. No shaft has been shown to rise toward it. No passage on the exterior aligns clearly with its position. These scans reveal missing density, but the architecture surrounding that absence remains hidden. This is what makes the space truly unreachable. It is not simply closed by a block that researchers can identify and perhaps remove. There is no confirmed barrier because there is no confirmed access route. Somewhere above the Grand Gallery, the stone gives way to a substantial volume, yet every surface that might define it lies beyond sight. The investigators know the approximate neighbourhood, but not the safest direction from which to approach it. The Grand Gallery seems like the obvious starting point. The void lies above it, and the gallery's roof is the nearest accessible architectural surface beneath the anomaly. Yet near does not mean thin. The corbelled walls rise through overlapping courses, and the masonry above them may contain multiple layers of structural stone. The exact thickness separating the gallery from the detected space is not established uniformly along its length. Drilling upward from the wrong point could pass through important load-bearing blocks, miss the target entirely, or enter a smaller gap unrelated to the main anomaly. The gallery's height creates practical difficulties as well. Reaching its upper surfaces requires scaffolding or specialized equipment inside one of the pyramid's most constrained and heavily protected spaces. Any machinery must pass through narrow corridors and operate without damaging ancient masonry. Dust, vibration, anchoring, and the removal of drilled material all become conservation concerns. Even a very small borehole must follow a path chosen with far greater precision than the current muon images can guarantee. Approaching from above is even less realistic. The void lies deep beneath the pyramid's sloping outer faces. A vertical or angled route from the exterior could cross tens of meters of masonry. Such an intervention would be destructive on a scale no modern conservation program would accept. It would also provide no certainty that the drill encountered the intended volume at a safe point. The pyramid's exterior is not an expendable shell surrounding an interior prize. The outer mass is part of the monument's archaeological evidence. A route from the king's chamber or the relieving spaces above it might appear possible on a sectional drawing, but the detected region is separate from those known features. The relieving chambers form a vertical stack immediately above the king's chamber, while the big void lies over the grand gallery. No passage between them has been detected. The masonry separating these areas may contain complex structural arrangements, and forcing a connection would risk confusing two independent architectural systems. The narrow shafts rising from the Queen's and King's chambers offer no confirmed solution. Their courses are known well enough to show that they do not simply lead into the big void. Some extend toward the exterior, while others terminate at blocking stones and contain bends or small spaces of their own. They are far too narrow for human movement and difficult even for specialized robots. Although their existence proves that the builders incorporated hidden channels into the pyramid, they cannot be treated as convenient service routes to every unknown feature. The well shaft presents a similar temptation. Its irregular path connects the upper passage system with the lower descending corridor, showing that concealed movement routes existed during or after construction, but it lies below and away from the big void. No evidence links the two. The presence of one obscure shaft does not imply a hidden network extending throughout the monument. This absence of access raises a deeper question about intention. If the big void was a chamber meant for ritual use, storage, or burial, how did ancient workers enter it? A usable space normally requires a route, even if that route is later sealed. Perhaps an entrance exists but remains too narrow or too deeply buried for current scans to resolve. Perhaps it connects to a passage filled with stone, whose density makes it nearly invisible against the surrounding masonry. A corridor packed after construction would no longer create the strong low-density signal of an open route. It is also possible that access was temporary. Builders may have entered the space while the pyramid was rising, then closed the route as additional courses were placed above or beside it. In such a sequence, the void could have been reached from an open construction surface rather than through a permanent internal corridor. Once the surrounding masonry was completed, no doorway would remain. The space might never have been intended for later entry. That possibility fits some structural and construction explanations better than ceremonial ones. A temporary working cavity, lifting corridor, or load management space could perform its function during building and then become inaccessible without requiring a formal entrance. The relieving chambers above the king's chamber were technically reachable during construction, but most were not designed as rooms for normal movement. Hidden architecture can exist because the monument needed space at one stage, not because future visitors were expected to enter it. Still, the scale of the big void complicates this interpretation. A minimum length of roughly 30 meters represents a major decision, whether the space is continuous or divided. Leaving such a volume inside the pyramid required control over the masonry around it. Even an accidental or irregular gap of that size would reflect a construction process, unlike the tightly packed solid mass commonly imagined. The evidence remains incomplete, but the anomaly is too substantial to dismiss as an ordinary crack. Another possibility is that the axis lies beyond the current resolution of the scans. Mography detects large density contrasts particularly well, but a narrow corridor can be difficult to distinguish when surrounded by thick stone. If a small passage approaches the void at an angle poorly covered by existing detectors, its signal may merge into the background. More viewing positions and higher resolution tomography could reveal a thin extension that earlier measurements missed. This is one reason future mapping matters more than immediate entry. Before a probe can be considered, researchers need to know whether the big void is close to any accessible surface, whether its nearest boundary is stable, and whether a narrow connection exists. A three-dimensional model built from many muon angles could transform a broad zone into a more precise architectural target. Ultrasound or another technique might then examine the final meters from a nearby chamber, if such a chamber can be identified. The contrast with the north-face corridor is revealing. That hidden space lay only a short distance behind the pyramid's outer surface. Multiple techniques narrowed its location, dimensions, and depth until investigators could select a precise point for a tiny opening. The camera entered because the pathway from known surface to unknown cavity was short and carefully mapped. The Big Void is larger, deeper, and surrounded by far more uncertainty. Its detection solved the first problem whether a substantial low-density space exists, but left the root problem almost untouched. Until that changes, the void remains separated from the human world by more than stone. It is separated by incomplete geometry. Researchers cannot knock on a door because no door has been found. They cannot place a camera against a wall because they do not know which accessible wall, if any, lies closest. They cannot assume the space is safe to enter, or even that it has a floor capable of receiving a probe. The Great Pyramid has concealed many features through blocking stones and vanished entrances, but the Big Void presents a more absolute form of isolation. It is present enough to measure and distant enough to resist inspection, an internal place known without any confirmed path by which ancient or modern eyes might reach it. Once a large low-density space is accepted as real, interpretation begins to divide. The same signal can support several architectural possibilities, and each one changes the story of the pyramid in a different way. The Big Void may be a chamber, a corridor, a structural cavity, a construction space, or several smaller gaps that current scans blur together. The evidence is strong enough to require explanation, but not yet sharp enough to choose one. The most immediately compelling possibility is a chamber. Human imagination prefers rooms because rooms imply purpose. A chamber may have been designed for ritual, storage, burial equipment, symbolic architecture, or a function that has no surviving parallel. The pyramid already contains carefully planned rooms with distinctive materials and forms, so another deliberate interior space would not be impossible. Its position above the Grand Gallery might even suggest that it belonged to an upper architectural sequence now hidden from every known route. Yet the word chamber carries assumptions the scans do not support. A chamber normally has identifiable boundaries, walls, a floor, a ceiling, and some relation to an entrance. None of these has been directly resolved. The muon data identify reduced density over a substantial distance, but they do not show a rectangular room or a formal enclosure. Calling it a chamber may therefore be useful for popular description, but scientifically it moves ahead of the evidence. A corridor is another possibility, especially because the detected extent appears long. If the space runs in a narrow, continuous direction, it could resemble a second gallery or an inclined passage. Such a feature might have helped move materials or workers during construction. It might also have served as a route that was later blocked or abandoned. The Great Pyramid contains several passages that slope at precise angles, and the Grand Gallery itself combines movement, structure, and perhaps construction logistics. A long hidden corridor would fit the monument's broader habit of embedding circulation routes within masonry. The difficulty is orientation. Existing measurements do not clearly establish whether the void is horizontal, inclined, or divided. A corridor that parallels the Grand Gallery would suggest one type of engineering logic. A horizontal space crossing above it would suggest another. A steeply inclined passage could be part of a lifting or construction system, while a level corridor might connect areas not yet detected. Without a sharper three-dimensional image, these remain models rather than discoverers. Structural explanations are less dramatic but perhaps more consistent with the pyramid's mechanical demands. The Grand Gallery creates a large open cut through the core. Any structure above such a void must redirect immense weight. The corbelled walls already move pressure outward, but additional cavities or carefully arranged gaps might further control how forces travel through the masonry. The relieving spaces above the king's chamber demonstrate that the builders understood the value of leaving empty volume where direct loading could threaten a room below. Recent studies of the pyramid's dynamic response reinforce the importance of hidden spaces in structural behavior. Measurements taken in chambers, passages, and the known relieving spaces show that internal cavities affect how the monument responds to vibration and seismic forces. This does not prove that the Big Void was designed as an earthquake protection system, and no study has established its function. It does show that open spaces inside the pyramid are mechanically significant. A void above the Grand Gallery could alter stress paths whether or not that was its original purpose. If the Big Void is structural, it may not be one large room at all. It could consist of multiple separated cavities created by rows of inclined blocks, overlapping roofing systems, or irregular packing above the gallery. From a limited number of viewing angles, several aligned gaps might merge into a single long anomaly. In that case, the scans would be correctly detecting low density, while the popular image of one enormous empty chamber would be misleading. A construction gap offers another explanation. The pyramid was built in stages, and every stage required temporary access. Workers had to transport stone, position blocks, manage tools, organize teams, and maintain routes as the monument rose. Some working spaces may have been filled later. Others may have remained because sealing them offered no advantage or because they became enclosed before completion. A long cavity could preserve a construction route that was never intended to appear in the finished design. Internal ramp theories have made this possibility especially attractive. Some models propose that builders moved blocks through corridors or ramps within the growing pyramid, rather than relying only on vast external ramps. A hidden linear space might appear to support such an idea. However, the Big Void does not by itself prove any internal ramp system. Its exact shape, slope, endpoints, and connection to construction levels are not known. A theory must explain more than the existence of empty volume. It must show how that volume functioned within a workable building sequence. Counterweight systems have also been proposed. The Grand Gallery's height, central channel, side benches, and regular sockets have led some researchers to suggest that it supported a mechanism for moving heavy stones. A cavity above or near it might have belonged to such an arrangement. Again, the possibility is intriguing but unconfirmed. No preserved machinery, rope traces, anchor system, or directly connected space has been identified. The architecture permits hypotheses, but it does not yet select among them. There is also the possibility of a design change. The pyramid's interior may preserve abandoned plans, just as the unfinished subterranean chamber suggests that construction decisions evolved. The builders could have begun one internal route and later replaced it with another. A cavity above the Grand Gallery might be the remnant of an earlier chamber, passage, or roofing scheme that was enclosed when the plan changed. Such alterations are known from other Egyptian monuments, where corridors were redirected, rooms enlarged, and burial arrangements revised during construction. If so, the Big Void may be important not because of what it contained, but because it records a moment when the pyramid became a different building from the one first imagined. It could preserve the ghost of an abandoned design, sealed not for secrecy, but because construction moved on. More irregular explanations must also remain open. Differences in core masonry, loosely packed zones, natural gaps between large blocks, or collapse within an ancient cavity could contribute to the signal. However, the anomaly's size and repeated detection make a purely ordinary masonry irregularity difficult to accept without a specific structural model. A scattering of small joints would not normally produce a coherent excess, extending for roughly 30 meters, unless those joints formed an unusually organized low-density zone. No single explanation fully accounts for the available evidence. A ceremonial chamber struggles with the absence of a known access route. A corridor lacks confirmed orientation and endpoints. A relieving space must explain its unusual scale. A construction cavity requires a plausible building function. A cluster of smaller gaps must reproduce the strong, extended muon signal. Each interpretation solves one part of the puzzle and leaves another exposed. This is why greater resolution matters more than a more dramatic theory. If future scans show one continuous volume with regular boundaries, the chamber or corridor interpretations will strengthen. If they reveal several separated cavities above the gallery, a structural explanation may become more likely. If a narrow extension leads toward an accessible region, the question of entry will change completely. Shape is not a decorative detail. Shape is the evidence that can distinguish purpose. For now, the Big Void remains suspended between categories. It is too large to ignore, too poorly defined to name with confidence, and too deeply buried for easy inspection. The pyramid offers just enough information to show that something deliberate or structurally significant may lie above the grand gallery, while withholding the form that would explain why it was left there. The north face corridor offers something the Big Void cannot yet provide: a complete journey from an invisible anomaly to a visible architectural space. It is smaller, closer to the surface, and entirely separate from the great low-density region above the Grand Gallery. But its discovery shows how modern investigation can move from particle data to direct observation without turning the pyramid into an excavation site. The corridor lies behind the large chevron-shaped blocks above the original entrance on the north face. Those angled stones have long attracted attention because their arrangement suggests an effort to redirect weight away from something beneath or behind them. The visible entrance lower down already has its own protective masonry, yet the higher chevrons seem to mark an additional structural concern. For generations, they encourage speculation about a hidden cavity, but visible form alone could not prove that one existed. Muon detectors supplied the first strong evidence. Measurements indicated a low-density region behind the chevrons, distinct from the known descending passage and separate from the Big Void. Because the suspected space lay near the exterior, researchers could observe it from several practical positions. The geometry was more favourable than the deep region above the Grand Gallery, and the thickness of stone between the detector and the anomaly was far smaller. Continued muon measurements gradually refined the feature. By 2023, researchers were able to characterize it as a corridor-shaped space approximately 9.06 meters long, just over 2 meters wide, and a little more than 2 meters high. In some measurements, the statistical confidence exceeded 10 sigma, leaving little doubt that the anomaly represented a real internal volume rather than ordinary variation in the masonry. Even so, the muon data did not immediately justify drilling. The scans showed where the corridor probably lay, but a safe intervention required more than an approximate location. Investigators needed to understand how close it came to the outer surface, where its boundaries were, and which stone could be crossed with the least risk. A few centimeters of error might mean striking a structural block, entering at an unstable joint, or missing the space entirely. Ground-penetrating radar was used to examine the masonry behind the chevron area. Reflections suggested boundaries consistent with an open cavity. Ultrasonic testing provided a second form of measurement, sending mechanical waves into the stone and recording where the signals encountered changes. Numerical simulations helped researchers compare possible shapes and depths with the observed data. Rather than producing one perfect image, each method reduced the range of uncertainty. The key was convergence. Tomography suggested a hidden volume. Radar identified reflective boundaries. Ultrasound responded to changes compatible with a cavity. Three-dimensional modeling aligned the results within the same region behind the north face. Later work combined these datasets through multimodal image fusion, allowing researchers to compare their overlapping strengths rather than treating each scan as an isolated result. Electrical resistivity tomography added another independent test. By measuring how electrical current moved through the stone, researchers could distinguish relatively solid masonry from a region dominated by air. The resulting model indicated an air-filled zone beginning close behind the surface and extending inward. It did not replace the earlier methods. It strengthened the case by detecting the same feature through a different physical property. Only after this sequence of measurements was a small opening approved. The chosen bore was narrow enough to limit damage and carefully positioned according to the combined scans. Through it, an endoscopic camera entered the hidden space in 2023. For the first time, the corridor ceased to exist only as a pattern in scientific data. The images showed a rough, empty passage beneath a pointed ceiling formed by angled limestone blocks. Its width and height closely matched the dimensions inferred from the scans. The surfaces were unfinished compared with the carefully dressed stone of the king's chamber or grand gallery. No inscriptions, burial equipment, treasure, or obvious doorway appeared within the visible area. The corridor ended in a stone wall whose relationship to deeper architecture remained uncertain. The visual confirmation was scientifically important not because the room contained something spectacular, but because it validated the chain of methods that had located it. Tomography had detected the density difference. Radar and ultrasound had refined the position. Modeling had identified a safe path. The camera had then shown that the invisible anomaly corresponded to a real architectural cavity. This case also demonstrates how cautious terminology can evolve with evidence. Before the camera entered, researchers could describe a corridor-shaped structure because the measurements constrained its geometry unusually well. After direct observation, corridor became a visual fact rather than only a reconstruction. Its ceiling, surfaces, scale, and emptiness could be documented. The word no longer depended entirely on interpretation. The Big Void has not reached this stage. It remains known through muon measurements alone. Its position is much deeper, its boundaries are less precise, and no accessible outer surface lies only a short distance away. The successful opening of the north face corridor does not imply that investigators can repeat the same operation above the Grand Gallery simply by choosing another wall and drilling. The difference in depth changes everything. The northern corridor began roughly a meter behind part of the exterior masonry, making near-surface radar, ultrasound, and electrical measurements possible. The Big Void is surrounded by far greater thicknesses of stone. Techniques that performed well near the north face may lose strength, resolution, or interpretive clarity before reaching it. A camera requires not merely the existence of a space, but a known path from an accessible surface to its boundary. The northern corridor also possessed a visually suggestive external marker. The chevron stones indicated an unusual structural arrangement, and provided a limited area for concentrated investigation. The Big Void has no comparable mark on the exterior. Nothing on the pyramid's visible faces clearly announces where the unknown volume begins, or how it might connect with the known interior. Its successful exploration nevertheless offers several lessons. The first is that muon anomalies can represent genuine architectural spaces. Critics of the Big Void cannot simply dismiss mography as incapable of detecting hidden features, because the northern corridor was found, measured, and later seen. The second lesson is that particle data alone do not complete the discovery. Direct access became possible only after multiple non-destructive techniques agreed on position and shape. The third lesson is patience. Years separated initial detection from camera confirmation. That delay was not a failure of technology. It was the time required to turn a broad anomaly into a conservation-safe intervention. The monument's importance demanded more than curiosity. It demanded evidence strong enough to justify altering even one small point in its masonry. The fourth lesson is that direct observation may produce a quieter answer than the imagination expects. The hidden corridor did not reveal a royal burial or an untouched archive. Its emptiness did not make it meaningless. It may protect the original entrance from pressure, form part of a load-relieving system, or preserve a construction feature whose function scholars still debate. A space can be archaeologically important without containing objects. That may eventually prove true of the Big Void as well. If it is ever observed directly, its significance may lie in stone arrangement, roof form, orientation, or structural relationship rather than treasure. A camera might show a vast finished gallery, but it might equally reveal rough masonry, several divided cavities, or a narrow construction zone. No single outcome can be assumed in advance. The north face corridor therefore serves as both encouragement and warning. It shows that the pyramid's hidden architecture can be mapped and carefully reached. It also shows how much work must occur before one tiny camera can cross a wall. For the Big Void, the scientific journey has confirmed the destination but has not yet found the final route. To understand why the pyramid might contain a large hidden space with no known entrance, it helps to stop imagining the monument as a finished object and begin imagining it while it was still rising. The Great Pyramid was not created all at once. For years, perhaps decades, it existed as an unfinished construction landscape of ramps, working platforms, exposed chambers, temporary routes, lifting zones, storage areas, and partially completed masonry. Every interior space known today was once open to the sky or accessible from a construction surface. The sealed monument is only the final state of a far more complicated process. That process required the builders to solve two problems simultaneously. They had to raise an enormous mass of stone, and they had to preserve open rooms inside that mass without allowing the weight above to crush them. The two goals were inseparable. Every chamber removed material that would otherwise carry load. Every passage interrupted the continuity of the masonry. Every roof needed a way to redirect pressure towards stronger areas. The King's Chamber shows this principle most clearly. Its granite ceiling is formed from massive beams, but those beams do not carry the full pyramid directly. Above them, 5 low cavities and a final pointed roof help redistribute the weight. These so-called relieving chambers were never decorated or designed for ordinary use. Some are so low that movement inside them is difficult. Their purpose lies in the relationship between stone and force, not in human occupation. The Grand Gallery uses a different solution. Its walls rise inward through corbelled courses, narrowing the opening as they ascend. Each level projects slightly over the one beneath it, carrying part of the load outward rather than allowing the entire mass to press vertically onto the passage. The gallery's form is therefore both visual and mechanical. Its soaring interior is produced by the same geometry that protects it. A hidden volume above the gallery could belong to this system. If the builders left an additional open region beyond the visible corbelled roof, that space may have reduced the amount of direct weight above the gallery, or allowed loads to spread across a wider zone. It might be a continuous cavity, several parallel gaps, or a sequence of spaces created by inclined blocks. From the perspective of structural engineering, the void would not need to resemble a usable chamber. Its value could lie entirely in what it prevents the stone from doing. Recent studies of the pyramid's dynamic response help show why this possibility deserves attention. Instruments placed in known chambers, corridors, and relieving spaces reveal that open volumes affect how vibration moves through the monument. The cavities above the king's chamber influence the mechanical behavior of the surrounding structure. This does not prove that the Big Void was designed to resist earthquakes, nor does it establish a modern engineering calculation in the minds of the ancient builders. It does demonstrate that hidden spaces are not passive emptiness. They alter the way forces travel through the pyramid. Ancient builders did not need equations of structural dynamics to learn this. They had generations of experience with stone construction. Earlier pyramids had cracked, shifted, been altered during building, or required changes in angle. The bent pyramid at Dashur records one of the most visible adjustments, its slope changing partway upward. Whether that change resulted from structural concerns, construction timing, or several factors together, it shows that pyramid building was not a single perfect invention. It was a developing practice shaped by observation and correction. By the time Khufu's pyramid was built, Egyptian architects had inherited lessons from mastabas, step pyramids, and earlier true pyramids. They understood that large roofs required careful support. They knew that angled stones could divert pressure. They used corbelling, granite beams, pointed ceilings, and strategically placed cavities. The hidden architecture of the Great Pyramid may preserve some of the most advanced results of that accumulated experience. Masonry sequencing may be equally important. A space cannot simply be removed from the middle of a completed pyramid. It must be created while the surrounding courses are built. Workers would place side walls, roofing blocks, and supporting masonry in a planned order. Temporary access might remain open until the final roof was set. Materials could be moved through routes that later disappeared behind additional courses. If the Big Void was part of a construction sequence, its lack of a permanent entrance becomes easier to explain. The space may have been reached from above while the pyramid was still incomplete. Workers could enter it from an exposed platform, use it to position blocks or manage lifting operations, and then seal the approach when construction advanced. Once the higher courses were added, the cavity would remain trapped inside the monument without any need for a corridor connecting it to the finished interior. This possibility also applies to temporary ramps. The exact system used to raise the pyramid remains debated. External ramps, zigzagging routes, levering, hauling teams, internal passages, and combinations of methods have all been proposed. No single model explains every stage with complete certainty. A long internal void could appear to support an internal ramp theory, but that conclusion would be premature. A working ramp would require specific dimensions, slope, turning space, entry points, and relationships to construction levels. The Big Void's geometry is not yet known well enough to test those requirements. Still, construction routes do not need to resemble modern hallways. They could have been rough, narrow in some areas, wider where blocks were maneuvered, and modified as work progressed. A cavity left by such a system might look irregular or divided. its final form could reflect practical decisions rather than architectural symmetry. Counterweight systems offer another possible connection between engineering and hidden space. The Grand Gallery's steep incline, central channel, side ledges, and repeated sockets have long encouraged theories that it was used to move heavy granite blocks through a system of ropes, sledges, or counterweights. A cavity above it might have provided clearance, anchoring space, or part of a larger mechanism. Yet the evidence remains incomplete. No preserved device confirms this interpretation, and the gallery may have served several purposes over the course of construction. The pyramid's builders also had to manage tolerances. Blocks were large, but not perfectly uniform. Internal joints could shift slightly from one course to the next. Spaces left between structural elements may have been packed with smaller stone or mortar, while others remained open. A large muon anomaly might therefore combine planned cavities with irregular construction gaps. The boundary between design and practical compromise may not be as sharp as modern observers expect. Roof protection is perhaps the most conservative explanation. The Grand Gallery is an extraordinary opening, and protecting it required more than forming an attractive ceiling. Additional spaces above could separate the visible roof from the full mass higher in the pyramid. The builders may have created a hidden buffer zone, just as they created relieving spaces over the king's chamber, but on a longer scale suited to the gallery beneath. If so, the Big Void may be one of the pyramid's most important engineering features despite never being intended for entry. Its meaning would lie not in what was placed inside it, but in the fact that the Grand Gallery still stands below it after more than 4,000 years. The empty space would be part of the monument's strength. This interpretation remains only one possibility. The current scans cannot show whether the void follows the gallery's slope, sits horizontally above it, or breaks into several volumes. But engineering offers a crucial correction to the assumption that every hidden space must have contained something. In a monument built from millions of tons of stone, emptiness can be a tool. The Big Void may eventually reveal an unknown passage or chamber. It may instead reveal the invisible architecture that allowed the known spaces to survive. Until its shape is mapped more clearly, both possibilities remain open, and the stone mountain keeps the difference concealed. The Big Void entered public imagination almost as soon as it entered scientific literature. A large hidden space inside the Great Pyramid was always going to attract stories, especially when no camera image existed to limit them. The absence of direct observation created a perfect surface for projection. Into that unseen volume, different audiences placed treasure, royal burials, sacred archives, lost technology, and secret knowledge withheld from the world. None of those claims is supported by the current evidence. The muon scans reveal a substantial low-density region above the Grand Gallery. They do not reveal a sarcophagus, a mummy, a statue, a doorway, an inscription, or a collection of objects. They do not show that the space was sealed after a burial ceremony. They do not identify a route through which funerary equipment could have been moved. Even the claim that the void is a single chamber remains unproven. Before anything can be said about its contents, its form must first be established. The idea of a hidden burial chamber is understandable, because the Great Pyramid is generally interpreted as the funerary monument of Khufu. The known king's chamber contains a granite sarcophagus-like box, yet no royal body or burial assemblage survives there. This absence has encouraged the suggestion that the true burial room lies elsewhere, perhaps in a space deliberately hidden more effectively than the visible chambers. That possibility cannot be ruled out in the absolute sense, but there is no positive evidence connecting the Big Void to a burial. Its position above the Grand Gallery is unusual for a royal chamber as understood from other Old Kingdom pyramids. No known passage approaches it. No blocking system has been identified. No funerary text, architectural marker, or associated object points toward it. A missing body in the king's chamber does not automatically relocate the burial to every newly detected cavity. The same problem applies to claims of treasure. Ancient Egyptian royal burials could contain valuable equipment, and the pyramid was certainly a target for robbery. But mography cannot distinguish an empty space from one containing a modest quantity of objects. It cannot detect gold, wood, textiles, or stone containers at the resolution needed to identify them. To say that treasure may survive somewhere inside the pyramid is speculation. To say that the Big Void contains it is invention. The legend of a hidden library or archive reaches even further beyond the evidence. Stories of secret records beneath or within Egyptian monuments have circulated for generations, often linked to imagined repositories of ancient science, astronomy, or knowledge from a lost civilization. The Great Pyramid is frequently placed at the center of such traditions because its scale and precision appear to invite an explanation beyond ordinary human institutions. Archaeology offers no reliable evidence for such an archive inside the Big Void. The pyramid belongs to a well-documented tradition of Egyptian royal monument building, quarry marks, construction crews, surrounding cemeteries, workers' settlements, administrative remains, and earlier pyramids all connect it to the society of the Fourth Dynasty. Its engineering is remarkable, but remarkable does not mean inexplicable or non-Egyptian. The unknown space may refine understanding of that engineering. It does not erase the historical context that produced the monument. Claims of lost advanced technology often begin with genuine uncertainties. Scholars still debate the exact systems used to lift blocks, organize ramps, sequence construction, and manage the interior. The Big Void adds another unresolved feature. From there, some arguments leap from incomplete knowledge to hidden machinery, energy systems, or technology beyond anything known from ancient Egypt. This reasoning confuses absence of a complete explanation with evidence for an extraordinary one. The fact that researchers do not yet know the void's purpose does not make every proposed purpose equally plausible. A structural cavity, construction route, abandoned passage, or unknown architectural feature fits the known setting more directly than a machine for which no components, tools, residues, texts, or parallels survive. Another recurring claim is that authorities already know what lies inside and are deliberately suppressing the discovery. Delays in access are treated as evidence of secrecy rather than conservation. The careful language used by researchers is interpreted as avoidance. The absence of a camera is presented as proof that a camera must already have entered. Such claims misunderstand both the technical problem and the public record. The Big Void lies deep within the monument, and no safe entry path has been identified. The successful examination of the north face corridor required years of muon measurements, radar, ultrasound, modeling, image fusion, official review, and a precisely placed microscopic opening. The Big Void is more difficult by nearly every relevant measure. Caution is not surprising. It is the expected response when the structure being investigated cannot be repaired if a mistake is made. Official restraint also reflects the difference between scientific detection and archaeological interpretation. A physicist can report an excess of muons with high confidence. An archaeologist cannot responsibly call that excess a burial chamber without additional evidence. An engineer may model a structural cavity while acknowledging that the geometry remains uncertain. Different disciplines ask different questions, and responsible conclusions often sound less dramatic than the public wants. The media can blur these distinctions. A void becomes a room because room is easier to visualize. A room becomes a secret chamber because secrecy creates attention. The chamber becomes sealed, then royal, then filled with treasure, even though each step adds a claim not present in the original data. By the time the story reaches a headline, the cautious scientific phrase previously unknown low-density space may have disappeared entirely. This does not mean imagination has no place in the story. Hypotheses are necessary. Researchers must propose possible shapes and functions in order to design new measurements. Engineers may test whether a cavity reduces load. Archaeologists may compare its position with known pyramid architecture. Historians of construction may ask whether it preserves a temporary route. The important distinction is between a hypothesis that can be tested and a conclusion announced before testing begins. A useful hypothesis makes predictions. If the Big Void is a long corridor, improved tomography should reveal continuous boundaries and a consistent orientation. If it consists of relieving spaces, scans may show several separated volumes above the gallery. If it is part of a construction system, its slope and endpoints should fit a plausible building sequence. If it is a formal chamber, future imaging may reveal regular geometry or a connecting passage. Each explanation must eventually face the shape of the evidence. Unsupported theories often avoid that discipline. When one prediction fails, the claim shifts. A missing entrance becomes proof of superior concealment. An empty camera view becomes evidence that treasure lies behind another wall. The theory survives because no possible result can disprove it. That is not how the Big Void can be understood. The most responsible position is also the most intriguing. A large space exists where no space was previously known. Its minimum length is substantial. Its exact geometry, purpose, access route, and contents remain unknown. These statements are secure enough to transform the internal map of the pyramid and limited enough to preserve the mystery honestly. The Great Pyramid does not need a hidden archive or impossible machine to remain extraordinary. Its confirmed architecture already demonstrates organization, material transport, surveying, stoneworking, and structural planning on an immense scale. The Big Void adds to that achievement because it may preserve a part of the builder's design that modern observers have not yet learned to read. What lies beyond the evidence should remain open, but it should remain clearly beyond the evidence. The darkness above the Grand Gallery is not a blank check for every legend. It is a scientific unknown, and protecting that distinction may be the only way the eventual answer can still surprise us. Reaching the Big Void may not begin with a drill. It may begin with a better image. The present muon measurements establish that a substantial low-density region exists above the Grand Gallery, but they do not define its architecture closely enough for a safe intervention. Before any physical access can be considered, researchers need to reduce uncertainty about the space itself. Is it one long cavity or several separate volumes? Does it follow the slope of the gallery below? Is it horizontal, inclined, or irregular? How close does it come to an accessible surface? Does a narrow corridor connect it to another part of the pyramid? Each answer changes where an investigation could begin and whether entry is practical at all. The next generation of muon imaging is designed to approach these questions through tomography rather than simple projection. Existing detectors observe the pyramid from a limited number of positions, producing density maps from particular lines of sight. A more complete tomographic system would collect measurements from many angles around the monument. The principle is similar to reconstructing a three-dimensional object from numerous shadows. One view reveals where material is missing along a path, Many overlapping views can begin to separate depth, shape, and orientation. Simulations published in recent years have explored detector systems that could move along more than one side of the pyramid. By gathering muons from changing positions, researchers could test whether the Big Void is continuous and determine how its boundaries shift across the monument. A region that appears as one elongated signal from below might divide into multiple cavities when viewed from the east and west. A suspected horizontal chamber might instead emerge as an inclined passage. Greater angular coverage could transform the current broad anomaly into a genuine three-dimensional model. Larger detectors would also improve resolution. One proposed system would use muon telescopes with sensitivity roughly 100 times greater than the earlier equipment. More detection area means more particle tracks collected over the same period, allowing researchers to distinguish smaller features and reduce the time required for useful measurements. Such a system could operate outside the pyramid, avoiding the difficulty of carrying large instruments through narrow internal passages. This remains a technical proposal rather than a completed survey. Building, positioning, calibrating, and operating detectors of that scale around Giza would require major coordination. The surrounding plateau is an active archaeological and tourist site. Equipment placement must avoid obstructing the monument, affecting its presentation, or interfering with conservation work. The detectors would also need precise surveys and long exposures to produce reliable tomographic data. Even a high-resolution muon model may not be enough by itself. Once researchers identify the closest likely boundary of the void, other technologies could be applied from a nearby accessible surface. Phased array ultrasound may help determine block thickness, fractures, joints, and reflective surfaces in the final meters between a known chamber and the hidden space. Recent testing in the King's Chamber has shown that shear wave arrays can detect features several meters behind visible granite surfaces and reconstruct the arrangement of lower block courses without core drilling. Applying similar methods near the Grand Gallery would be more difficult. The masonry is limestone rather than uniformly accessible granite. The corbelled geometry complicates sensor placement, and the distance to the Big Void may vary. Still, ultrasound could help answer a crucial local question: what lies immediately behind the wall or roof from which a probe might eventually enter. Electrical resistivity and radar could also contribute if future scans locate a boundary close enough to reach. Their usefulness decreases with depth and complex masonry, but they may refine the final approach once tomography narrows the target. Image fusion would again be essential. A safe entry point would not be chosen from one bright region in one dataset. It would emerge where muon tomography, ultrasound, radar, electrical measurements, and structural modelling all support the same geometry. The monument's mechanical condition must then be considered. A hidden cavity is part of the pyramid's load-bearing system, whether it was intended for structural use or not. Drilling into its wall could cross a stressed block, loosen a fractured surface, or alter the distribution of the local pressure. Engineers would need to model the route of the bore and understand the masonry around it. Dynamic studies of the known chambers show that internal spaces influence vibration throughout the structure. The Big Void cannot be treated as an isolated bubble waiting harmlessly behind a wall. Material conservation adds another barrier. Studies of the inner chambers reveal salt deposits, mineral changes, humidity effects, and differences between limestone and granite surfaces. A space sealed for more than 4,000 years may possess its own microclimate. Introducing outside air could alter moisture, temperature, or salt behavior. A small opening might seem insignificant, yet it could create a long-term path for airflow, through a previously isolated zone. For this reason, the first physical contact would probably be extremely limited. The north face corridor was examined through a narrow borehole large enough for an endoscopic camera. A similar principle might eventually be used for the Big Void, but only if researchers identify a short, stable, and precisely mapped route. The bore would need to avoid decorated surfaces, ancient markings, important joints, and structurally critical blocks. It would also need to enter at an angle that allows a camera to see rather than merely touch the edge of the space. A conventional endoscope could provide basic images if the cavity lies close enough. Its lens might reveal roof form, wall texture, dust, block arrangement, and whether the space continues beyond the entry point. It could confirm whether the Big Void is one open volume or a sequence of smaller cavities. Even a limited view might distinguish carefully dressed masonry from rough construction packing. A fixed camera would still have serious limitations. If the space is long, divided, or irregular, a lens at one borehole may see only a small portion. A wall could block the view while the main cavity extends beyond it. Lighting would be difficult, and dust close to the lens could obscure more distant surfaces. Direct observation might therefore begin without producing a complete answer. Small robotic systems offer a more ambitious possibility. Engineers have proposed a miniature inflatable flying robot that could pass through an opening only a few centimeters wide. Once inside, the device would expand into a lightweight blimp and move through the enclosed space with cameras and sensors. Because it would float rather than crawl, it might avoid disturbing dust or placing weight on an uncertain floor. The concept is visually compelling, but it remains untested in the Big Void. A hidden cavity may contain sharp edges, narrow constrictions, loose stone, or separated compartments. Radio communication through thick masonry would be difficult. The robot would need to carry power, lighting, navigation, and a reliable return system while remaining small enough to pass through the bore. Losing a device inside the pyramid would create both archaeological and conservation problems. Tethered robots may be safer, though less mobile. A flexible cable could provide power, communication, and retrieval, but it might snag on rough stone or limit movement around corners. Crawling robots could inspect floors and walls if the surfaces are stable, yet their contact might disturb fragile material. Any robotic design would have to assume uncertainty rather than a smooth, empty chamber. The best path forward may therefore remain incremental. First, collect more muon angles, then reconstruct the void's three-dimensional form. Next, compare that model with structural simulations and scans from the nearest accessible surfaces. Only after the geometry, masonry condition, and conservation risks are understood could a microscopic opening be considered. The question is no longer simply whether technology can penetrate the stone. It can. The harder question is whether investigators can reach the unknown space while preserving every layer of evidence between the known world and the void beyond it. The Great Pyramid still withholds its complete shape. For all the measurements taken across its faces, passages, chambers, shafts, and hidden cavities, the monument has not become fully transparent. The Big Void is the clearest proof. It is large enough to alter the accepted internal map, strong enough to appear in several independent muon datasets, and yet distant enough to remain untouched by light. Its existence is established more securely than its identity. That distinction may define the next era of pyramid research. Earlier explorers often entered first and interpreted later. Modern investigators increasingly reverse the order. They model, scan, compare, simulate, and wait. The goal is not merely to reach an unknown space. but to understand enough of the surrounding structure that reaching it does not erase the evidence. In a monument where every block may carry structural, archaeological, and historical information, restraint becomes part of discovery. The most important unanswered question is shape. If future tomography reveals one continuous volume with regular boundaries, the Big Void may deserve a more architectural name. It could prove to be a gallery, an abandoned passage, a hidden chamber, or a formal space unlike anything else in the pyramid. If the signal separates into multiple cavities, the interpretation may shift toward load relief, roofing systems, or construction gaps. If a narrow extension appears, it may reveal a route once used by workers and later sealed. Each possibility leads to a different history of how the pyramid was built and why its interior took the form that survives. Its relationship to the Grand Gallery remains central. The two features occupy the same broad region, but similarity of position does not prove similarity of function. The known gallery is carefully finished, steeply inclined, and integrated into the passage system. The Big Void may parallel it, cross it, sit above it, or break into spaces that merely project as one from existing detector angles. What survives in the particle data suggests scale, but not finish. The difference between a polished corridor and rough relieving cavities cannot be read from muons alone. The newest non-destructive studies elsewhere inside the pyramid show how that uncertainty may gradually shrink. Ultrasonic shear wave arrays in the King's Chamber have mapped hidden joints, rear surfaces, and reflective features behind accessible granite. Material studies in the inner rooms have shown why the stone cannot be treated as an inert obstacle. Mineral alteration, salt crystallization, moisture, and ancient surface conditions all influence what interventions are safe. Dynamic measurements have demonstrated that known chambers and relieving spaces affect how the monument responds to vibration. Together, these studies make one point clear: an unknown cavity cannot be separated from the structure that surrounds it. This also changes the meaning of access. Reaching the void is not simply a matter of proving that a drill can cross limestone. It requires deciding whether a bore should exist at all, where it could pass with the least risk, what environmental change it might create, and whether the information gained would justify the intervention. A camera view would be extraordinary, but a poorly chosen route could damage a structural block, disturb an ancient joint, or open a sealed microclimate that cannot be restored. The North Face corridor provides hope because it shows that direct observation is possible when evidence converges. Yet it also sets a demanding standard. Its path from anomaly to image required years of tomography, radar, ultrasound, modelling, electrical resistivity, image fusion, official review, and precise drilling. The Big Void is deeper, less clearly bounded, and farther from any obvious surface. Its exploration will require not simply repeating the Northern Corridor investigation, but extending it into a more difficult class of problem. That may involve larger muon telescopes positioned around the pyramid, gathering many more tracks from many more angles. It may involve detectors moving along different sides of the monument, building a true tomographic reconstruction, rather than a limited projection. It may involve new algorithms capable of separating connected cavities from one another. Only then might researchers identify a boundary close enough for ultrasound, radar, or electrical methods to examine the final meters. Even after that, the first image may not resolve the mystery. A camera could enter a rough cavity and reveal only a nearby wall. A robotic probe could find that the space divides into smaller compartments. The void might contain nothing except construction debris and unfinished stone. It might have no doorway because no doorway was ever intended. Its importance may lie in engineering rather than ritual, in the survival of the Grand Gallery rather than any object hidden above it. There is quiet lesson in that possibility. Archaeology often celebrates what ancient people placed into space's bodies: offerings, tools, paintings, inscriptions. The Big Void may instead teach through absence. Empty volume can be part of a design. It can redirect pressure, preserve access during construction, isolate a roof, mark a change of plan, or hold the memory of a temporary stage later sealed inside the finished monument. A space need not contain treasure to contain information. This is also why the word void should remain in use until stronger evidence permits another. It protects the discovery from becoming a conclusion too early. A void is measurable without pretending to know its purpose. It leaves room for engineering, ritual, construction, accident, and revision. It acknowledges that the pyramid still contains forms modern observers have not learned to classify. The Great Pyramid has always stood between certainty and imagination. Its dimensions can be surveyed, its stones sampled, its passages mapped, and its historical setting reconstructed. Yet the monument also invites speculation because much of its interior remains inaccessible. The Big Void sharpens that tension. It is not a legend waiting for a proof. It is a proven anomaly waiting for interpretation. Perhaps future scans will reveal a second gallery suspended above the first. Perhaps they will show a chain of relieving cavities built to protect the corbelled passage below. Perhaps a narrow route will lead toward an abandoned construction space. Perhaps the geometry will be stranger than any present model. Scholars still debate these possibilities because no direct image has settled them, and no single explanation fully accounts for the evidence. What is certain is already remarkable. A space at least roughly 30 meters long escaped direct detection through centuries of exploration. It remained hidden not behind a named door, but within the mass of the monument itself. Its discovery required physics developed thousands of years after the pyramid was built, instruments capable of counting particles from the sky, and a willingness to accept that a strong result can still be incomplete. The pyramid therefore remains unfinished in the modern mind. Not unfinished as a monument, but unfinished as a map. Every new technique adds another layer without dissolving the mystery entirely. Thermography reveals unusual behavior. Radar and ultrasound define nearby boundaries. Electrical resistivity distinguishes air from stone. Muons cross the full mass and expose missing density. None of these methods sees everything, but together they make the invisible increasingly precise. One day, a camera may finally cross into the Big Void. Its light may fall across rough blocks, a narrow passage, a pointed roof, or a long darkness continuing beyond view. The first image may confirm a theory or overturn all of them. It may show a space built for people, or one never intended to be seen. Whatever appears, the discovery will matter because the route to it was careful enough to preserve the questions as well as the answers. Until then, the void remains where it has remained for more than 4 millennia above the Grand Gallery, beyond every known passage, present in the data and absent from human sight. And so, the story ends not with an opened door, but with stone. The plateau grows quiet as evening moves across Giza. The pyramid's faces lose their hard daylight edges and become broad plains of shadow. Visitors leave the passages. Instruments are removed or left to count in silence. Inside, the known chambers return to darkness, just as they have after every generation of explorers. Far above the narrow route through the monument, the unknown space remains unchanged. No lamp touches its surfaces, no voice enters it. Dust, if dust lies there, is undisturbed. The space holds no obligation to match the names given to it from outside. Chamber, corridor, gap, gallery, or void are words from a world that has never seen it. That distance is part of its meaning. Human beings build, seal, forget, rediscover, and name again. They leave marks in stone, but stone also keeps what it refuses to reveal. Time removes entrances, purposes, languages, and certainty, while preserving shapes that outlast the people who made them. The Big Void is one of those surviving absences. It reminds us that knowledge does not always arrive as possession. Sometimes it arrives as a boundary drawn more clearly. We know that something is there. We know approximately where it lies. We know that it is large. Beyond that, the darkness remains honest. Perhaps that is enough for now. Above the Grand Gallery, within the weight of millions of blocks, an unseen space continues through the pyramid. Cosmic particles cross it. Detectors wait below. The ancient stone holds its shape around the emptiness, and the emptiness holds its silence. Outside, night settles over the plateau, and the pyramid becomes what it has always been, a monument visible from far away, and a world within itself that no one has completely entered.